Welcome to The Explainer. Today, we are exploring something absolutely crucial, yet completely invisible, the geographical coordinate system. You know, when we look at a globe, we see the obvious stuff, right? Land masses, oceans, but superimposed over all of that is this incredibly complex web of imaginary lines. And these aren't just arbitrary markings on a piece of paper. They actually form a silent, mathematical engine that runs almost everything in our modern world. I mean, from the flight path of a commercial airliner to the exact microsecond timestamp on your last digital bank transfer, literally everything relies on this global grid. Okay, let's dive right into this. Think about it. This invisible grid takes a wild, rotating rock hurtling through space and transforms it into a highly structured, searchable map. Without this shared language of location, navigating the Earth would just be sheer chaos. By laying down this precise grid of latitude and longitude, early cartographers, and the modern geodetic architects who followed them, gave us the ability to pinpoint any location on Earth with absolute precision. And, maybe even more importantly, they gave us a way to perfectly synchronize global time.
So here is our navigational flight plan for today. We'll be looking at the world's invisible architecture, latitude and climatic destiny, longitude and the global clock, step-by-step time calculations, and, finally, powering modern digital infrastructure.
All right, kicking things off with Section 1, the world's invisible architecture.
And this brilliantly illustrates the foundation of it all. To truly grasp the scale of this system, you have to remember that it's designed to bring mathematical order to a massive spinning sphere. It's built on two foundational pillars. First, you've got latitude. These are the horizontal, parallel lines running east-west that never, ever meet. They just stack up, measuring your distance north or south from the equator. Then you've got longitude. These are the vertical semicircles we call meridians. They run north-south and actually converge right at the poles, measuring your distance east or west from the prime meridian. They're two completely distinct axes, but you put them together, boom, you've got exact pinpoint coordinates.
Moving right along to Section 2, latitude and climatic destiny.
You know, geography students will often call latitude the reliable ruler of the planet. And the reason for that all comes down to this number, 111 kilometers. Because lines of latitude are parallel and literally never intersect, the physical distance between each degree stays perfectly, reassuringly constant. One single degree of latitude is always going to equal roughly 111 kilometers. It does not matter if you're trekking across the Sahara Desert or freezing out on the icy plains of Antarctica. It's a steady, reliable measurement of north-south displacement.
But here's the thing. Latitude does way more than just measure distance. It actually dictates what we call your climatic destiny. Since the Earth is a sphere, your latitude directly determines your angle of solar incidence. Basically, how directly the sun's rays are hitting you. And this creates three massive heat zones. The torrid zone, locked right there between the tropics of Cancer and Capricorn, gets blasted with direct, intense sunlight year-round. Move a bit further north or south into the temperate zones, and you start seeing moderate weather and distinct seasonal shifts in daylight. Keep pushing past 66.5 degrees, and you hit the frigid zones, permanent, extreme cold, and wild, long periods of total darkness or total daylight. So yeah, your latitude literally decides your climate.
Which brings us to Section 3, longitude and the global clock.
Now, if latitude is our trusty, predictable ruler, longitude is the planet's giant, complex, and sometimes dangerous clock. Notice how all those vertical meridians curve and smash together right at the poles? And they all pass through that 1-0 point at Greenwich, England. Why Greenwich? Well, simply because Britain was the dominant maritime power back in 1884 when this was formalized. So it became the absolute zero, the ultimate global reference point for Coordinated Universal Time, or UTC.
So the crucial point here is that longitude operates on a shifting scale. Down at the equator, the distance between two meridians is nice and wide, roughly 111 kilometers, just like latitude. But as a ship sails north or south, those invisible lines pinch together. The physical distance shrinks until it's absolute zero at the poles. Now imagine you're a ship captain. If you fail to account for this meridian convergence, it can be catastrophic. If you miscalculate those shrinking degrees, your fuel consumption projections will be off, your arrival times will be wildly inaccurate, and navigational safety completely goes out the window.
And directly opposite the prime meridian, clear on the other side of the globe at 180 degrees, we hit the international date line. Think of this as the mandatory seam of our spherical planet. Because the Earth is constantly spinning, we geometrically have to have a physical line where one calendar day officially ends and the next one begins. It's essentially real-world time travel. You cross it heading west towards Asia, you've got to add a day to your calendar.
cross it heading east towards the US, you subtract a day. It is an absolute logistical necessity to keep global commerce perfectly synchronized.
All right, let's get into the math. Section 4, step-by-step time calculations.
Say you're an aviation pilot managing a long-haul flight path. Knowing exactly how to calculate these time differences on the fly is non-negotiable. And really, everything just starts with the rotation of the Earth. Our entire system of global chronometry is just a direct, simple calculation of the planet completing one 360-degree rotation every 24 hours. The math is honestly incredibly elegant.
If you take those 360 degrees and divide them by 24 hours, you get this beautiful, perfect constant. Burn this into your memory right now, 15. Every 15 degrees of longitude equals exactly 1 hour of time. Break it down even further, and 1 single degree of longitude equals exactly 4 minutes. That right there is the golden ratio of our global clock.
Now, in aviation and navigation, there's a simple standard operating procedure to follow. East gains, west loses. Why? Because the Earth rotates eastward. So, locations to the east experience the sunrise first, putting them ahead in time. So if you're calculating for a spot east of where you are, you add time. If it's west of you, you subtract time. Easy to remember, right?
Let's move to a real example and see how this builds. Imagine you're at 30 degrees west and your local time is 8 a.m. You need to figure out the time at your destination, which sits at 60 degrees east. Step 1. Find the total span. 30 degrees west plus 60 degrees east gives us a total gap of 90 degrees. Step 2. Convert that to time. 90 divided by that magic number 15 gives us 6 hours. Step 3. Apply the rule. Since our destination is east, it gains time. 8 a.m. plus 6 hours? Boom. The local time at your destination is 2 p.m. Simple, perfect mathematical logic.
Let's zoom out now for our final part, Section 5, powering modern digital infrastructure.
Because these calculations, they aren't just for pilots and geography students. The stakes are unbelievably high for every single one of us. Seriously, I want you to imagine this scenario. What if this ancient framework of imaginary lines just suddenly ceased to function today? What if our shared language of spatial orientation just vanished?
The scary reality is, our entire 21st century life would instantly paralyze. The mathematical logic we just walked through is the silent engine powering all of this. I'm talking GPS translating data to your smartphone, the military executing flawlessly synchronized tactical operations, complex aviation safety networks keeping planes from colliding in midair, and weather models predicting hurricane paths based on those latitudinal heat zones. Every single one of these depends entirely on this grid.
Now, what's really interesting about this slide is perhaps the most invisible reliance of all, the financial sector. High-frequency trading and global digital banking absolutely rely on GPS timestamps acting as the backbone for their infrastructure. Every single transaction happening across the globe has to be synchronized down to the microsecond. These systems use the exact math of the prime meridian and longitudinal offsets to agree on when a trade actually occurred. Without those precise calculations, the global stock market would literally suffer an immediate, catastrophic synchronization collapse.
So the next time you're looking at a map, or you just quickly check your phone's location, take a second to remember the sheer scale of the geodetic grid running quietly in the background. It is an absolute masterpiece of human ingenuity. It turned a wild, spinning rock into a synchronized, functioning global community. And I want to leave you with this final thought to ponder. Given how deeply interconnected our world is, just how vulnerable are we? How would we possibly survive the loss of our invisible architecture? Thank you so much for joining me on this explainer. Keep wondering, and I'll see you on the next one.